Good day, everyone, and once again, you're welcome to another quiz. Today we'll be treating groups. I'll be giving you the definition of a group. We have group abelien, that's a group commutative, and the likes. And hopefully, as we proceed, we'll be able to ride on the same bus and get to our final destination, of course, together. Thank you, and now we can begin. So we can define a group as a group G, we call the group G, associated with its loi de composition, étoile. This étoile, it means it's a loi. During, like, in some examples, you might be given maybe something like this, or even the normal multiplication, addition, but it's best for us to note it as a loi, because sometimes it might not be the exact addition that you know. It might just be because the loi will be defined with something. That's the important thing. It will be defined with, let's say I have a loi like this, étoile, and they say x étoile y, such x étoile y, such that the loi is defined as 2x étoile 2y, for example. The whole idea is that this loi will be defined for you with something like this, you see. So that's why we just call it a loi. It might not be the normal multiplication, it's just a loi. So a group G associated with its loi de composition, ça verifies the following properties. If it verifies these four properties, which we say is the loi de composition interne, associative, élément neutre, inverse ou symétrique. If it verifies these four properties, then we can say that it is a group. In place of saying G and then this, I can simply say G étoile. So what do we mean by it being defined as a loi de composition interne? It means if I have my elements in G, which G is a set. G is a set. If I have, for example, two elements in G, let's say A or B, or X or Y, the loi, when I apply the loi, those two elements, with the loi, the element should remain in G. It should not go to another set, maybe R or Z, or I don't know. We're just assuming it's a group G. We're calling it a general set. We know that G is not. We can't say G. We can't associate G with. We can associate G with R, G with Z. We are just noting G as a general set, depending on the particular type of set you'll be given. So G is like a general notation for these different sets that we know. So this is what we have. We have for every X, for example, for every X, Y in G, okay, when we associate it with the loi étoile, which we have here, étoile star, that's this, it would be X étoile Y must remain in G, okay, X étoile Y, it must remain in G. If it goes to you find out that it doesn't remain in the set, then it doesn't possess in loi de composition interne. And remember, the whole idea about a group is that it cannot verify one and then the other three will not be verified, or it cannot verify 1, 2, 3 and then the symmetry cannot be verified. The four must be verified, like they must be true. If one is not true, then it is not a group. Okay, so for associative, toujours, always, we are working with X and Y and in a set G. So if we have for every X, Y, Z appartient à J, Why did I include Z? Because when we're dealing with associative, generally when we're dealing with associative, we're dealing with 3 elements. If it's a couple, that's if it's in like this, it will be, let me say, X, Y, Y, X prime, Y prime, X prime prime, Y prime prime, tout appartient à G. That is if it is a couple. Here we are giving a general example, so we can scrap this out for now. So if I have 3, the whole idea is that you will have 3 set of elements. You get. So here we have X, Y, and Z. This is putut. Putut, that's for every element from our quantificators. For every X, Y, Z in G, because appartient probably for those, like, okay, I said this in G, that is X, Y, and Z, they are found in G. So for every X, Y, and Z found in G, X étoile Y étoile Z is equal to X étoile Y étoile Z. If it can verify this property, then it is associative. That is the associativité à gauche, at the left, and associativité à droite. You verify for X étoile Y étoile Z, X and étoile à gauche, that is at the left, and then you come and verify X, you bring it out, étoile, Y étoile Z, you verify à gauche, à droite, that's at the right. And if you can verify this, if this part is equal to what you have here, this is égalité, equal to, if they can verify themselves, then this one verifies this à gauche et à droite, that means it is associative. Now, element neutre. For element neutre, I need just one element from G to verify. Let's say I need X. I need just one, because for every element, if I should apply an element neutre, if there exists an element neutre and I apply that element neutre to that element X, I should get back my X. What am I trying to say? Let me do it somewhere around here. If maybe I have 5 and then I multiply 5 with 1, this is not it one now, and I multiply 5 with 1, I should get 5, meaning this 1 will stand as element neutre, because for whatever X that I have, if I multiply it with its element neutre with 1 for multiplication, I will get that same number. If I have for addition now and I have 5, what number will I add to this for addition that will give me the same element 5? It's 0. So even if I say 6 plus 0, I will get 6. 19 plus 0, I will get 19. 19 times 1, I will get 19. What do we notice here? That 1 is now the element neutre for multiplication, and 0 is the element neutre for addition. So that's why now I apply it like in a general sense. It's exactly what we're doing here. So for element neutre, let's say for every X appartient à G, which is true because I changed like different numbers, 5, 6, 19, and when I started with an element neutre, I still got the same number, the same X. So for every X in G, there exists an element neutre which we call E, small e, which we call an element neutre. There exists an element neutre qui appartient aussi à G. That element neutre should also be in that ensemble, that set that you are working with. In this case, we are saying G. So for every X appartient à G, there exists an E appartient à G. What can we, let's guess from here. So let's say this is X, right? Let's call this X. And we say times 1, let's call it E. What did we get? We still got X, right? We apply the same law here. For every X appartient à G, there exists an E that is also in G, such that X étoile E is equal to X and E étoile X will also give me X. Why? Because even if I say here we have 5 times 1 equal to 5. If I say 1 times 5, it will also give me 5. So even if my element not is here étoile X, it will still give me X. You get? So this is why we say element not. This is element not in the right side and element not in the left side. And if I find my element not in the right side, it has to be equal to the element not in the left side. It has to also, the two, they have to verify themselves. If the element not here is different from the one that is here, then it doesn't have an element not, because it has to be unique. If the element not exists, it has to be unique, both à gauche et à droite, that is both in the left side and in the right side. So that's for element not. Finally, we have for inverse or symmetric. Just like I did here, I'll give another example. If, for example, I have, let's look for multiplication and addition, for example. Now I have 5 times something should give me 1, because we're working with the inverse. So what is the inverse of 5 in multiplication? It's 1 over 5, right? Because if I do this and cancel this, I will get 1. Let's choose another number. Let's choose 8. I have 8. 8 times 1 over 8. If I cancel and cancel this, I'll get 1. And 1 is what? What do we say 1 is for multiplication? Is the element not, right? So this is equal to the element not for multiplication. If I do it for addition, what was our element not for addition? We said 0. So if I have 8 here and I add it, remember it's for addition. What will I add here and put here that will give me the element not, which is 0 for addition? Negative 8. Because if I say 8 plus negative 8, I will get 0. So the symmetric or the inverse for 8 is negative 8. The inverse or the symmetric for 8 in multiplication is 1 over 8. And whatever you do with the symmetric, you will get what? The element not. That's exactly what inverse and symmetric is trying to say. So in this case, that is, yeah. So let's do our general definition. We'll say for every X appartient à G, remember I just need one element to verify, there exists let's say X prime, or you can say X bar, appartient aussi à G, remember it must remain in that ensemble, such that X étoile, remember that is the law we're working with, X étoile X prime will give us what? E, the element neutre. That is, this is now at the right hand side, and also X prime étoile X should give us element neutre, because even if I say 1 over 8 times 8, I will still get 1. Minus 8 plus 8, I will still get 0. So at the right hand side and the left hand side, it should be verified. So at the end, what have we gotten from definition of this? We've said that it should have a group. It is said to be a group if it verifies the loi de composition interne, associative, element neutre, and inverse or symmetric. Now there is one more thing is something we call the group abelien. Groupe abelien, to prove, they tell you montrer que cette loi de composition interne associée avec une groupe quelque chose associé avec une loi de composition interne, montrer que c'est un groupe abelien. To prove that it's a group abelien, tout simplement, you verify these four properties. You verify that it's a lot of composition interne, associative, element, neutre, inverse, symmetric, and in addition to these four, the fifth thing you will now verify is that that it is commutative. And what does it mean, like being commutative? If I have always, for every x, y appartient à j, x étoile y should be equal to y étoile x. Or if I have it in coupled form, like when I said that x y and x prime y prime, that means it should be x y étoile x prime y prime. It should be equal to x prime y prime étoile x y. If it verifies it, then it is commutative. If you prove this four and then you prove commutative, and then the law, it's not, the law that you're giving is not commutative, you simply say that it is not a group abelian. It's a group, but it's not a group abelian. So you can say it's a group non-commutative. Yes. And then one final thing is, just write it here just for you to know. If I have x étoile y moins 1 is equal to y moins 1 étoile x moins 1. Not x moins 1 étoile y moins 1. It's y moins 1 étoile x moins 1. It's a very important remark, and you should take note of this. So that's how we have for our definition of group. See you in the next video. Thank you.